So I developed a CodeQL library in queries to help with detecting iterator invalidation. So I guess first, like, who am I? I'm an incoming senior at Montgomery Blair High School. I worked as an intern this summer for Trail of Ticks, and I do a lot of bug hunting and CTF playing, and I'm also an organizer for Angstrom CTF. So I've invested a significant portion of my time into just like learning this stuff, and I had a lot of fun this summer working on it for a job, I guess. So I'll jump right into some background. An iterator is just an object in C++ that references an element of some container. So that's like a vector or a list or something. And the iterator supports two basic operations. It can be incremented to access the next iterator in the container, or it can be dereferenced to get the underlying element of the container. So here's some example code that's just like a common pattern where iterators are used. Is you have a for loop where you get the begin iterator with vec.begin. You get the end iterator with vec.end for your end condition of the loop. And then each iteration, you increment the iterator to get the next element. And so this, for example, would just turn out 1, 2, 3, 4, 5. C++11 added this fancy new syntax that kind of hides the iterator behind the scenes. So it expands to basically what we had above. The compiler does this, and it dereferences it for you and everything and increments it for you, and it's very nice. But it also kind of hides the iterator, which makes the bug even more subtle. And once again, it'll print out 1, 2, 3, 4, 5. So then the bug comes when you invalidate the iterator before like some usage of it. And according to the spec, this is undefined behavior when you do something to a container, and it's container specific what invalidates it. But for example, if you like add a new element to the container, that could mess with the implementation of iterators, and now you get undefined behavior. And in practice, what this is it's it's usually something to do with the container's backing store. So for example, when you go vec.pushback, you're adding a new element, and if the vector is already at capacity, you now have to allocate a larger backing store, and then you'll free the old one. But the iterators on the vector are pretty much just pointers, and you now have a pointer to freed memory, so you have a use after free. Another case where iterators are invalidated in vectors is if you erase an element. And this is the implementation in libstdc++ of vector erase. It shifts everything past the iterator to the left by 1. So you overwrite the iterator with the next element, everything else is shifted back, and then you decrement the end. And it makes sense why the iterators, it invalidates every iterator at and beyond the iterator that was erased according to the spec, and you can see why that's the case based on this implementation. And I'll give an example where erase results in like memory corruption later in the talk. So then finally, we need to like know what CodeQL is. It's a query language that developed by Semel, which was then bought by GitHub for static analysis of like code. And one of the languages that they support is C++, and they have very comprehensive standard libraries, including like variables, expressions like incrementation, and even global data flow tracking, like interprocedural, this value goes where type stuff that is very, very useful. And it can be used to find dangerous code patterns. So like iterator invalidation, or here a simpler example, mismatched array sizes, where you just take a function call and a function that takes an array as a parameter, and then in C, the compiler doesn't actually care like what size the array is. So you could pass two different array sizes. You could pass a smaller array to a function that expects a bigger one, and you'll get some memory corruption if you'll get some out-of-bounds access, but the compiler doesn't know that. But you can use CodeQL to detect that by checking if your array size on the function call is bigger than the array size in the parameter. So now we'll get into what I actually worked on, which I deemed Iterator. It's a CodeQL library for iterators and iterator invalidation. So there are 4 classes that I wrote that are useful. There is iterated, which is a variable access of a collection in a situation where you're retrieving an iterator from it. So this would be like vec in vec.begin. Then you have an iterator, which is pretty self-explanatory. It's a variable that is of an iterator type. You have an invalidator. So this is like some, I guess, some terminology that I coined. You have an invalidator and an invalidation. And the invalidator is the function call within the scope of the iterator, so like within a for loop's body, that will result in the invalidation, like somewhere down the line of function calls within that invalidator. Then the invalidation is like vec.pushback. It's the thing that actually messes up the collection, messes with the collection so that the previously created iterators become or could become invalidated. So then here is like the stuff that I am mostly running, or like you'll be running if you use this, is the queries. So I have invalidation flows, and it is the thing that gets the potential invalidations of iterators, the potential bugs. And I use their global data flow library to be able to get like very complicated bugs that, I mean, even like if I just read the code, I don't know if I would have seen it, some of the stuff I reproduced. And it does have a relatively high rate of false positives. And that's because of stuff like if you invalidate an iterator in a for loop, but then you break out of it somewhere later before you ever use the iterator again, then that's not an actual invalidation bug. Or if you reinitialize the iterator. And CodeQL can track control flow stuff, so you could detect that. And I like did have some detection code for that sort of thing, but then it gets really, really slow, right? Because you're just tracking like every code path and it kind of explodes, and it's just not manageable. I had like a 13-hour query that I had to just like give up on. So it turns out it's a lot easier just for the person looking at the query results to be like, okay, that is not a real invalidation, and then like they try to reproduce and they're like, okay, that's real. So there are a good amount of false positives, but it is a good trade-off for the performance improvements, and it's very manageable. So then the other query that's kind of a helper one is iterated types, and that just returns the types that are iterated over in the code base, because I already have the invalidation constraints for STLs written out for the STL types, so like vector, list, map, all that stuff written out. But then if you're iterating over something that is specific to your code base, like in LLVM, there's like a set vector, then you want to be able to define the specific invalidation constraints. And this will help you quickly know what to define those for. Okay, so now the fun part, bug hunting. So these were my steps. I looked on GitHub for some large C++ repository. I ran my query to see what the non-standard iterated types were and add those invalidation constraints. And then I just run the query and I go through the results and filter out false positives. And if I'm lucky, I end up with some bugs. So here is an example here's the erase invalidation on a vector. So it will read from a save file. This is like a roguelike with a few thousand stars on GitHub. And if in your save file, you put something like this in your zones save file, it will then see like test is not a valid type, and then it erases it. However, as you can see, they don't do anything to make the iterator valid again. So you have an invalidation. And here you can actually get a seg fault, because if you start the loop, your zones.end is like, I guess, index 1, where you only have one element. So you have like index 0, and then the memory past that is your end iterator. So then when you erase it, your end is shifted back by 1. And now it's equal to the address that you just had because of the implementation of erase that I showed earlier. And now when at the end of the loop you increment the iterator, you're now beyond zones.end. So you won't trigger the end condition, but it will still re-enter the loop, and you're now dereferencing just whatever random stuff was on the heap when it was allocated. So that is fun to get a seg fault. So here's a slightly more complex bug that I found. I was actually running the query on like the Swift compiler, but then when I built it, it also included all the LLVM sources, specifically Apple's fork of LLVM. And it actually turns out that upstream, it was fixed like a couple months ago unintentionally, when they rearranged like the undefined symbol logic, or really change the handling of it. But it's still it's like 12 function calls deep, and it was just very exciting to find, I guess, because it's like this is not a simple bug like the last one, where it goes through like LLVM bit code, which references like a dependent library, which is in a linker script, and then it adds that symbol as undefined. And as you can see here, the thing it's iterating over, config undefined, it then pushes back to it based on the undefined thing added in the linker script. So that is, and then you now have a use after free because the vector capacity was likely reallocated, because it does reallocate for the first for the first few capacities. And yeah, on the next iteration, you have a use after free, and that's exciting. So my, or I guess first, like just like any questions.